Looking at the notes, so go ahead and get the notes out in front of you, the new notes. All right, so first slide, guys, got some blanks to write down. Periodic table organization. So first off, how do we get the periodic table? Well, as you might expect, there was kind of the current version of this periodic table didn't always exist. There was sort of a simpler form of the periodic table that developed earlier, but the very first elements that were discovered were in this by the year 1700 we discovered 13 elements. So sometime in the 1600s, people had begun to isolate matter down to these essential elements, and they had 13 of them known by 1700. And then as in the 1700s, just scientific methods, technology got better. Scientists got better at isolating elements. So there came a need for organizing this knowledge, right? Once you have all of these elements, are there common properties that certain elements have? And there's a way to group them. If you're wondering what were those first 13 elements, they are highlighted here. So position where they would be positioned on our modern day periodic table. So there you go. We go on this slide. Got the blanks filled in. I actually am Gryffindor.
Hey, I'm a Slytherin.
You must know.
I'm a Slytherin.
You're a Slytherin? Yeah.
Hey,
Hey, judgment free zone. Everyone's a Gryffindor, I feel like.
No. Dude, I'm a Slytherin.
I feel almost ashamed being Gryffindor. I feel like I want to be different. It's bad business.
I'm telling you, I'm a Slytherin. Ravenclaw and Hufflepuff.
Ravenclaw and Hufflepuff are the big ones. It's just.
Okay, all right, moving on. You got some new blanks to write down?
You know which one is it?
The first scientist, guys. First scientist to propose a kind of a primitive version of the periodic table is Dmitri Mendeleev. So this is this picture here. This is actually the literal table he made, a picture of it. And he organized the elements by increasing atomic mass. Now, going back to Unit 1, why would that be an issue? Why would that be tricky to organize the elements by mass? Do I remember? Yeah, so we mentioned how argon and calcium both have a mass of 40. So every element could, not every element, but the mass number is not going to be unique for elements. It's actually the number of protons that's going to be unique. But you didn't know that at that point. You just did it by mass because measuring mass is something that they were able to do. We did finish right in there. All right, cool. So then this is what our modern version of the periodic table looks like. And again, we don't organize it by mass number. We're going to organize it by the atomic number. Now remember, the atomic number, that's the number of protons. So if that's not familiar to you, make sure you add that in. Atomic number, that's the number of protons. Okay? And broadly speaking, we organize the periodic table into periods and groups. Now, periods are going to run left to right, and groups go top to bottom. Okay? So groups are vertical, and then periods are going to be the horizontal ones. Okay? Now, this last bullet point is super important. You're going to star that for yourselves. Elements in the same group are going to share similar properties. So, meaning, if I said, hey, calcium, I'm trying to do a chemical reaction, I run out of calcium. And it's dang, I gotta do this chemical reaction. What element could I get that'd be similar to calcium? Well, you'd pick another element that's in that same group. So if you don't have enough calcium, maybe you could replace that with magnesium. Magnesium and calcium would behave similarly. They're not identical in their behavior, but they're gonna have very similar properties. And I've done that before. There's some reactions we had to do in class, and we don't have enough calcium metal, and I replace it with magnesium metal, and they behave more or less the same. Okay. All right, we good here? Okay. Now there are three general categories of elements. There are nonmetals, metals, and metalloids. So the majority of the periodic table is going to be metals. I don't know if you knew that. The majority of the elements on Earth are metals. And like you would say, like left to like bottom left would be the metals. And then there are these things called nonmetals that are going to be on the right portion of the periodic table, more towards the top right. And then there's an in-between. These in-between elements are called metalloids. So metalloids, they're really unique elements. They're very flexible elements. Sometimes they behave like metals. Other times they behave like nonmetals. And I'll go into a little more detail on those later. But I'll explain different properties in a couple slides here. But just keep in mind, you need to memorize that general pattern. So I would show you like a certain element. Like for example, phosphorus. What is phosphorus? Metal, non-metal, or metalloid? And you'd be expected to answer that. Okay. All right, moving on. So looking at the properties of metals, a lot of these, the hope would be they're common sense because, you work with metals every day of your life. Metals are going to be solid at room temperature, meaning you can melt metals, but you need to be at like super, super hot temperatures. Now, when you cut metals, they have a high luster. Luster, another like a synonym for luster would be sheen. Basically, it's like talking about shiny. So metals are shiny, and that should make some sense to you, right? Like, you've seen metals. Look at like the metal legs in your chair. You kind of see the reflection in there. And I would say they're pretty shiny, right? And again, they're the majority of the elements on the periodic table. Give me a minute to finish writing. All right, cool. A little more on metals. Metals are something called malleable. Malleable means you can hammer it into a certain shape. So sometimes you hear that word malleable used in maybe in English class to describe a certain character. Like so and so is really malleable. That means maybe they can be changed very easily. You can change their mind and stuff. And then ductile. Ductile, that word isn't maybe as obvious, but ductile means you can put it into a wire. Ductile means you can put it into a wire. So copper wire shown there. So just kind of a lot of vocab in this.
What else can you preach all metals?
Yeah. Generally, I mean, I'm sure there's some exceptions, but generally, yeah. All metals can be put into wires. Be pretty hard, but yeah. Okay, some more on metals. Metals are good conductors. Hopefully you've seen or heard that word conductor before. A conductor is something that moves heat and electricity very well. Meaning a good conductor can get hot really easily. That's why we use metal pans to cook on. They get hot really quick compared to other materials. And that's why metal wires are used for electricity. Now, why metals are good conductors has to do with electrons. Because what is electricity? I haven't taught you that, but from it has to do with electrons. Actually, it's the opposite.
Electrons fall apart.
Well, not fall apart, but movement. Electricity is the movement of electrons. So electricity is the movement of electrons. We'll come back to that at different points throughout the year. So if you're a material that can give up electrons easily, you're a material that lets electrons move easily, you would be then a good conductor. Whereas if you're a material that holds on to its electrons, you would not be a very good conductor. You would be what we call an insulator. Some of the details of conductors or insulators we'll get into a little bit later. I wouldn't worry about it so much now. Just kind of an introduction to the idea. Okay, moving on. Nonmetals. So most nonmetals are going to be gases at room temperature. So if you see a gas, chances are that's a nonmetal. Nonmetals in their solid state are generally brittle. Brittle means it falls apart pretty easily. So powders, most of your powders are going to be nonmetals. So for example, sulfur. Sulfur can will like crumble pretty easily. Even carbon. Anybody know? Now carbon's kind of an exception because carbon's solid. But what do you use carbon for every day? Carbon fiber, like right now. Oh, what are you using carbon? Lead. Yeah. Well, graphite. So like it'll, it's a form of carbon that will like, but it breaks apart pretty easily. That's why that's a good thing, right? You can use that to write your code and stuff. Yeah. What's up?
So, like, why, like, so for example, like, some metals, need, like, gases, or, like, gases, like, get,
Okay, so question was asked, hey, can some metals be gases? Generally speaking, no. They're going to be solids. They can become liquids if they're like super, super hot. But I'm not aware of metals becoming gas.
so they can't ever, like, get into, like, the air.
No, not that I'm aware of. There probably is some exception out there, but like generally speaking, you're not gonna get like metal gas. No. Yeah. Last thing is not malleable or ductile. So malleable means it bends easily. Ductile means it goes through a wire easily. So you're not making wires out of nonmetals. More things on malleable. Think of like swords. You make swords out of metal because you can like bend that metal into like different shapes. Okay. Talked about conductors and insulators. So nonmetals, they're not gonna have a luster. Remember, luster is talking about shininess. So nonmetals are not shiny. They're actually dull. You've heard that word, like so and so's really dull, meaning they're either kind of boring. So if something is dull in chemistry, it's a similar idea. It's just not shiny. It doesn't really like stand out. Okay? You're not making chains out of nonmetals, right? And nonmetals are going to be poor conductors, meaning nonmetals are not insulators. Or I'm sorry, nonmetals are insulators. Nonmetals are not conductors, they are insulators, meaning they do not conduct electricity. So if you're an insulator, you are not conducting electricity. The reason why they're good insulators is because they hold onto their electrons really well. You'll appreciate this more later on in the year, but these would be, what are these red circles here? Spheres. Oh, not protons. Electrons. So these are the electrons. So see how these electrons are like really are held tightly? They're held up in a bond, we would call. Whereas in metals, the electrons are free to move around. That's why they're good conductors. But we'll work on that as the year goes on. Okay, now metalloids. So I mentioned earlier that you have elements that are in between of metals and non-metals. So those are going to be the metalloids. Sometimes they're called semi-metals, like they're semi, they're like in between. And they're harder to identify in the periodic table. They're this blue little staircase. So boron, silicon, germanium, arsenic, antimony, tellurium, T, acetine. But you want to like identify that staircase. Okay. You can figure out the metalloids and everything else falls into place because to the top and right of the metalloids are the nonmetals, and then to the bottom and left are going to be the metals. Okay. Good here. All right, a little bit the properties of metalloids. Metalloids are called semiconductors. So, what's like a common name for California? We go to California called something Valley.
Oh,
Silicon Valley. Why do they call it Silicon Valley? So raise your hand. Raise your
Death
hand.
Valley.
Death Valley.
Is that somewhere else?
I think that's more like you said. I think that's part of Death Valley. California. Why do they call it California Silicon Valley? Somebody explain that for me. Silicon Valley.
Yeah, because that's what you make computer chips with.
Yeah, because that's where a lot of like the tech companies are, where they started, and tech companies they use computers and stuff, and computer chips are made of primarily silicone. So silicone, the property of silicone makes it very useful to make semiconductors. Now the reason is because when you have a computer, there are times when you want that computer to act like a metal. When you turn on your laptop, you want the electricity to flow through that laptop, and you want it to act like a metal, conducting that electricity. But there's going to be times when you don't want it, you don't want your laptop or certain parts of a circuit in your laptop to conduct that electricity. In that case, you want it to behave like a non-metal. And silicone will act like that. So, interestingly, germanium is actually pretty similar to silicone. How would you know that? How would you know germanium is similar to silicone? It goes back to the yes, but close together, same group. So it's all about meaning like viewers, like phosphorus is close to silicone, but phosphorus does not have very similar properties. They're in the same period. But silicone and germanium, they're in the same group. So it's almost germanium value. Like really, like they almost wasn't for like price, like silicone is easier to get to, like cost wise, but they could make chips out of germanium. I don't really know how, I can't personally make it, but like apparently, because they have similar properties, you can make semiconductors out of germanium. Okay. All right, now then, the first group of the periodic table, we call those the alkali metals. So there are your alkali metals. Some things you need to know about them. They are very reactive. So if you want to do a chemical reaction that is extremely reactive, you would want to do that reaction with an alkali metal. Alkali metals will always form +1 cation. So that's something you need to memorize, as well as they have 1 valence electron. Okay, so those are 2 things you got to memorize with the alkali metals. And because they are so reactive, they're rarely just found by themselves in nature, because they're going to want to react with some other element and form a compound, and that compound would then exist in nature. But the metal just by itself, it's possible, it exists, but it isn't as common to be found. All right, now then group 2. So then we're going from left to right. So now we're at the second group here, second column. Those are called the alkaline earth metals. So group 1 was alkaline, or alkali. Group 2 is the alkali or alkaline earth metals. Now these are also going to be very reactive. Not as reactive as group 1, but they're still going to be pretty reactive. They're kind of soft as far as metals go. That's a unique feature of them. They react pretty well with water, but so do the alkali metals. I wouldn't really call that a key property personally, but they do have 2 valence electrons. I really want to make sure you know that 2 valence electrons, and they form +2 cations. So it's actually kind of easy to remember, right? Because we're talking about group 2, so they form +2 cations, and I actually have a sticky note with those up there. And then 2 valence electrons. And similar to the alkali metals, they're not really going to be found in their elemental form in nature. They're usually found reactive with, bonded with something else because they're so reactive. Okay. All right, now groups 3 through 12. So it's like that rectangular looking thing on the periodic table. It's like you drop down into the valley. Those are called the transition metals. Now the reason why they're called transition metals is because we're transitioning from your like very like reactive metals towards your metalloids and then your nonmetals. So they're less reactive than your other metals. So groups 1 and 2, first two columns, those are the most reactive metals. Transition metals, yeah, I mean they react, but like that's why like silver and gold are on there, right? You don't want silver and gold in your chains, or you do want them in your chains, but that's because they're not very reactive. You don't want them reacting with your skin. You have a chain on, or you're wearing earrings, you don't want that reacting with your skin. That's why like cheaper chains or like jewelry would be made with like maybe like groups, really like group 3 or maybe like group 2. Like aluminum would be more reactive and it's gonna be a little bit cheaper. Anyways, all right. Now, if you go to the very bottom here, these two bottom rows, these are called the lanthanoids or lanthanides, and the actinoids are the actinides. We don't really like talk too much about. We don't really work with these elements as much. They're rare. You're not going to see them quite as often. That's why the lanthanoids are called the rare earth metals, because they're harder to find. You don't see them as much. Now you'll notice how like the setup of them, it's kind of weird. Like it's those like two random rows at the bottom of the periodic table, and because they're at the bottom of the periodic table, you might think they're like going to be the larger elements, but really these fit in right up here. So the lanthanoids and actinoids, they fit in at group 6 or at rows 6 and 7, but you don't want the periodic table to be like crazy wide. That's why they pull them out and stick them down there. So the periodic table isn't like, you know. Because otherwise, if you think about it, if you were to squeeze them in here, then it'd be like super wide. Not as like far down, but it'd be really, really wide. All the actinoids, they're radioactive. So like uranium, you hear about that with like a lot of like nuclear stuff. That's going to be an actinoid or actinide. There you go. It starts with La. Lanthanoid, you're like, where did they get that name for the first element in that row? La. Actinoid, AC. That's the first element in that row of actinoids. So the names actually kind of make some sense. F block, they do call them that. I'll explain why they call them that a little later on in the year. I wouldn't worry about that as much right now. Okay. Sometimes you'll hear them called the inner transition elements. All right, almost there. Group 7 is called the halogens. So we're kind of skipping the names of some of them in like group 3, you don't really have like a common name. It's with group 4, but halogens is group 7. Now sometimes they call it group 17. So where the 17 comes from is if you count starting from the left all the way to the halogens, you would count 17 columns. Now where the 7 comes in is if you go 1, 2, skip the transition elements, skip like the rectangle. 3, 4, 5, 6, 7, that's where the 7 comes from. Okay? Now, the group 7, the halogens, they also are very, very reactive. Now, the reason why they're really reactive is because they only need one more electron to fill their outside shell of electrons. Thinking back to the Bohr model, the electrons are in these rings, right? The valence shell is that outer ring. So, halogen, they need one more electron, then they have a completely full shell. And we'll keep referring to that throughout the year, but elements want to have a full valence shell. Elements are the most stable when their outside shell is full. So that's why halogens are really, really reactive. They want to pair up with something else. So they form -1 anions. So you want to make sure you know that. And I actually got a sticky note of it up there. Bless you. And they exist in nature as something called diatomic. So di means 2. So anytime you see these in nature, they're always paired up. So fluorine, you don't just see fluorine by itself, bless you, because it's really reactive, it's going to pair up with another fluorine atom, and it's going to be F2. And they form salts. So halogens will react very, again, they react very easily. They react with the alkaline metals especially well, and they form these salts. Ever heard of NaCl? Table salt. Cool. Okay. All right. Now, group 0, also called group 18 or group 8, are the noble gases. I'm sorry, there are 3 names for it, but understand that the names actually make some sense. So group 18 would be if you were to just count from left to right. You count all the columns all the way to the noble gases, you would get 18 columns. If similar to group 7, if you don't count the transition metals 3 through 12, you skip those, you would get 8. So that's where group 8 comes from. And then where group 0 comes from is that all of the noble gases do not need valence electrons. Meaning they have a completely full valence shell of electrons. So again, atoms are the most stable when they have a full shell of electrons. The noble gases have that. That's why we call them inert. And that's why we call them group 0. They need 0 valence electrons to be stable. Is that the last slide? Sorry that it's a little bit longer today. Just kind of is what it is. But yeah, you got a formative essay that maybe it's kind of tedious, but I don't think it's super hard. Just some practice questions, just trying to get you more familiar with the setup of the periodic table. Okay? Let me get everybody going, answer some questions, and I'll slowly get the tests out from last class.